This is section 9.8, power series. Okay, so today we're going to talk about a special type of series that can represent transcendental functions, and actually some algebraic ones as well, with an infinite series. And that infinite series is called a power series because it involves powers of x. As we saw in an earlier recording, we graphed various polynomial approximations of e to the x by adding more and more terms, which we got by equating, first of all, the function output for the function and the polynomial, and then we equated the first derivatives for the two, and then we equated the second derivatives, etc., and we kept building this. And the idea was that we could continue in this pattern until you got to the nth term, and that would be a good approximation of e to the x, centered at 0, and it got broader and broader as we had bigger and bigger n for where it looked like it was tracing right over. And as it turns out, if you actually continue that process forever, so that you have a complete infinite series.
I didn't quite catch that. Could you please repeat it?
Every time I say series, my phone thinks I'm talking to it. It's an iPhone, so you can probably figure out it thinks it's Siri. Anyway, sorry about that. So the infinite series, this power series, is something that we can use to represent e to the x. In fact, I think I said the other time, that's how calculators actually calculate e to the x, is with a finite representation of this, but technically if you were to go forever, it would be it exactly. So for every real number x, not just the ones close to 0, but every real number, it can be shown that this infinite series on the right converges to the number e to the x. So if you look at the definition of power series on that first slide after the introduction of the concepts we were going to cover, you'll see that a power series is any series that has this look to it. And we'll start with 0 for this, generally speaking, for the power series. So we want to start with a coefficient, a sub n, I wrote a 0. So I was thinking about the first one, which is going to start at 0. A sub n, x to the nth. And so the very first substitution with x to the 0, that gives you a constant like the 1 in the expansion of e to the x as a series. That's why we want to start at n equals 0. And you can also have something that looks like that. It does not have to be centered at c equals 0. That one is the one that I wrote first, but it doesn't have to be. It can be any coefficient that we want to describe. And by the way, the coefficient in that series for e to the x is that division by n factorial. That's the coefficient a sub n in that. And anyway, back to this, it could be centered elsewhere, and that means that every single term will have x minus c raised to the nth. And of course, when c is 0, that becomes just x to the nth, which is the first one I wrote. So, so this is a power series, the second one I wrote, that's centered at c, where c is just some constant value. So if you look at example 1, where you see a power series centered at 0, notice that x minus c has been replaced with x minus well, x minus 0 has been replaced by x, which is raised to the nth. And so that when it's x minus 0 raised to the nth, it'll look like x to the nth. That will always be centered at 0. And then b, you see the x plus 1 means it's centered at negative 1. And the x minus 1 in each of the terms in example C means that it's centered at positive 1. So if it were x minus 4 in each term, it would be centered at positive 4. If it were x plus 7, it would be centered at negative 7. So just kind of a heads up as to what that will look like when you're looking for the center. It should be an obvious x minus something that's in every term that you're going to see. And of course, if it's 0, it'll just be x to the nth. Now, we can think of the power series as a function of x by thinking of this as that polynomial expansion of the series. Of course, if you look up to the right, where I have e to the x equals, the right side of that is a function of x. And if we put something in for x, we could calculate and find out what e to that number is equal to. So, in general, think of this series as a function of x. And as such, the domain will be the set of all x for which the power series converges. And it's not necessarily all real numbers, so this is not a trivial statement about the domain of f. The power series has to converge for the x's that are in the domain. Now, if you think about it, every single series will converge at its center because f of c will be the series from n equals 0 to infinity of a sub n, and if you substitute in c where the x is, of course that's going to be c minus c to the n, which is going to be a sub naught times 1, because anything raised to 0 would be 1, plus, and every other term is going to be a 0. And so it converges to a sub naught. So every series converges to its center for sure. Okay? So that means that the center C is always going to be in the domain of f, and that may be the only thing that is in the domain. It might only converge to its center. So there are three different things that can happen. You could have if you think of the real number line as the representation of the domain, it could be, one of the cases is where the only number in the domain is that center. So it can converge to a single point, the center. The next thing that you will see that happens at times is that there will be an interval of convergence from something to something where C will be at the center of it. Okay, and so we're going to call the distance from the center to either edge the radius of convergence, r. And then the third possibility is that it will converge. Oops, I forgot to color in part of that other one. It converges for all of these numbers from r to the left of c to r to the right of c. It converges at all those numbers in that interval. And then, of course, the last possibility is that it converges for all real numbers. So its domain will be all real numbers. So the domain can be one point, a finite interval, or all real numbers. Those are the three possibilities. And that's outlined in Theorem 9.20. For a power series centered at C, precisely one of the following is true. converges only at C, so that one. The series, there exists a real number R, which is a positive number, such that the series converges absolutely for x minus C is less than R. And it will diverge otherwise. So I'm going to write that divergent part up here. Actually, let me change colors so that that's really clearly something different. Make that red. For something that looks like this, it would diverge for the absolute value of x minus C greater than R. And I want to continue with the idea of this absolute value inequality of where it converges that I've written in pink there. That, of course, is a representation without absolute value of x minus C being between the opposite of R and R. This is an algebraic concept of how you get rid of the absolute value in an inequality. When it's less than, this is what happens. And so if you add C to all three places, you end up having that the domain is from C minus R to C plus R, which is, of course, the interval that's shown up above. Okay. You might notice that there's one thing missing. When you're comparing the absolute value of x minus C to R, we've got greater than for divergence, less than R for convergence, and the third possibility is that the absolute value of x minus C is equal to R, which would be the endpoints of that interval. And that's going to be up for consideration. It's not stated in the theorem what happens there at R, at the ends of the interval. And so what we're going to have to do at C minus R and C plus R, we're going to have to test for convergence at the endpoints because the theorem doesn't address them. And that means we're going to have to test it. And the reason we'll have to test it is sometimes there is convergence when it equals R, and sometimes there's not convergence when it equals R. So that's going to be a little bit of extra work we're going to have to do in that particular case. And then the last one, of course, is that the domain is all real numbers. And so the domain would look like this, perhaps. Okay. So this R that I've been talking about, I think I already said this, but I'll repeat myself. R is called the radius of convergence of the power series. If it converges only at C, the radius of convergence is 0. Okay, we're not moving away from that point at all. If the series converges for all x, then the radius of convergence is infinity. So that radius from the center out would go forever as a distance away from C. The set of all values of x for which the power series converges is called the interval of convergence. Let me write that down here because we'll have different intervals of convergence. We're going to define I to be the interval of convergence. So when they ask us to find the radius of convergence, we'll be using the letter R, and that will be, part of our notation will be the R. And when they ask us about the interval of convergence, we're going to represent that answer with the letter I. All right. Let's see. Change colors here. So let's look at an example. The first example we're going to do is one where we find the radius of convergence. It's all that we're asked to do. But I'm going to be coming back to these examples and find the interval of convergence in just a little while after we find out how to do so. But for right now, let's just focus on the radius of convergence. And then we'll build on the interval of convergence as well. So I'm going to leave myself a little bit of room on the right, probably, to write that out. So, since the center of this one is 0, because x minus 0 to the nth would simplify to be x to the nth, we can test the center, of course, by putting in 0 and put that into our formula for x. That will become 0 to the nth, which is going to be 1 plus 0 plus 0 plus 0 equals 1, so it converges. Now, let's say that we fix x to be any constant, such that I fix the value of x to be some constant, such that the absolute value of that x is a positive number, so it's not 0. If I were to let u sub n equal the expression of our series formula, n factorial times x to the nth, then the limit as n approaches infinity of u sub n, the absolute value of n, u sub n plus 1 over u to the nth. And do you remember what that is the test for? When you take the limit of the absolute value of a sub n plus 1 over a sub n. Do you recall that one? Yes, it's the ratio test. Which, by the way, is pretty ubiquitously used in doing the type of problem where we're finding the radius of convergence. It's a really good test for this. Okay, so anyway, u sub n plus 1 will have us substitute in for each n with n plus 1. So that'll be n plus 1 factorial times x to the n plus 1 divided by n factorial times x to the nth. Now, of course, there's no guarantee here that x is positive. The absolute value of x is positive, but x itself does not have to be positive. So when we go to simplify this, I'm going to take this in several steps. As you gain confidence and experience, we may have fewer steps. But the n plus 1 factorial over n, if you'll recall, cancels out to become n plus 1. And the division of powers of x with the same base means we'll subtract the exponents. N plus 1 minus n is 1, so that becomes x to the first. Now, as far as this limit is concerned, n is the variable for the limit. N is changing. It's headed towards infinity. So when I split this up into two pieces like this, the absolute value of a product is the absolute value of one factor times the absolute value of another factor. That absolute value of x is considered constant for this limit because this limit's variable is n. And so I can pull that constant absolute value of x out in front. And of course, since n is 1 or bigger, the absolute value there is not needed. And so this is the limit as n approaches infinity of n plus 1. And as that heads toward infinity, this will become the absolute value of x times infinity plus 1 is infinitely large. And any constant, absolute value of x would just be some number, times infinity is going to be infinity. Especially if we've taken the absolute value, we know it'll be positive infinity, by the way. So that means that what we've used is the ratio test. So we'll say, therefore, by the ratio test, when we get an answer of infinity for this, that means that the series diverges. So the series in question, just write this out, of n factorial x to the nth diverges for the absolute value of any x being positive. So that means it converges only at its center, which was our first statement up there. So that means that this series converges only at its center, because it diverges for all other values of x. Of course, its center is 0. And that means that the radius of convergence is 0. Okay. So let's do some more examples. Like I said, we're going to come back in a little while and talk about the intervals of convergence. Just not quite yet, because I want to do all of these radius of convergence questions first, so we know that what we're focused on is radius of convergence for a little while. All right, so we have the square root of n times x to the nth that's under consideration. So, as I said before, we're going to use the ratio test. And if you remember, for the ratio test, we find the limit of the absolute value of a sub n plus 1 over a sub n, and if that answer comes out to be of a certain type, we'll know what of number or answer. We'll know something about this convergence. If that number, if that limit comes out to be less than 1, we know it converges. If it's greater than 1 or infinity, it diverges, which is what we used in the last example. If it comes out to be equal to 1, that ratio test is inconclusive, and we'll have to find some other way to test it for convergence. Okay, so let's set this up, the limit as n approaches infinity of the absolute value of that formula with first n plus 1, n for each n, divided by that formula as is with n in it. Okay. The absolute value of the square root of n plus 1 over the square root of n is just simply going to be the square root of n plus 1 over n, because that's not ever going to be negative. We don't need the absolute value. And we can combine those two radicals into one radical. And then the absolute value of x to the n plus 1 over x to the n, subtracting the exponents, we're left with x. But keep in mind that x needs to stay inside of the absolute value because we don't know if it's positive or negative. Okay. Then the limit of that square root of n plus 1 over n, remember that's that linear over linear, or same power, and you use the ratio of the coefficients to do this quick limit. So that's going to be the square root of 1 over 1, which is 1, and 1 times the constant absolute value of x is absolute value of x. Then the ratio test says that we'll have convergence when this limit, which there's our answer right there for the limit, is less than 1. So we're going to ask about, well, where is that going to happen? When will that answer be less than 1? That's where it's going to converge. Okay. Now, I want you to look at the theorem 9.20 really quickly again. That's where you saw the absolute value of x minus c less than r. And so when you see something in that form, which is what I see down here, the last thing I wrote down below is absolute value of x minus understood 0 is less than 1. That implies when it's in that form, we now know what r is. R is 1 for this problem. Okay, so the radius of convergence for right now for this is just the radius of convergence is 1. Okay, like I said, we're going to come back and do intervals of convergence later. So we answered the question that was posed. So let's go on to number 2. This is sigma. This time we're starting at n equals 1 and going to infinity. X to the nth divided by 5 to the nth times n to the 5th. So we're going to use the ratio test. By the way, we use that a lot. As I said earlier, it's the most commonly used way to find the interval, the radius of convergence and then the interval of convergence. The other one that's used sometimes is the root test, but the ratio test happens like 90-something% of the time, and that means the root test is only used, well, less than 10% of the time. All right, so here we go. We're going to set up our limit. So the limit as n approaches infinity of the absolute value of x to the n plus 1. Remember, we're substituting n plus 1 into the numerator version of this. So that'll be over 5 to the n plus 1 times n plus 1 to the 5th divided by, now in the denominator we use the regular version of this, just what you see up above, x to the nth over 5 to the nth n to the 5th. All right, so now we're going to deal with the division of two fractions by taking the numerator fraction and to divide it by another fraction, the denominator fraction. To do that division, we're going to change that into multiplication by the reciprocal of that denominator. Okay. So, let's see what we can do with this. Well, one of the things I see that we can do with it is we can deal with the powers of x. And to divide powers of x, you subtract the exponents. And so x to the n plus 1 divided by x to the nth will be x to the first in the numerator. For the 5s, they have the same base. There are more of them in the denominator, and if I cancel out n of the 5s, the numerator won't have any left, so it'll be times 1, and we'll have a single 5 left in the denominator. And that leaves n to the 5th and n plus 1 to the 5th because they're not the same base, so we can't subtract exponents there. Okay. Now the absolute value of x over 5 part can be split away from the things that involve n, and since n is 1 or bigger, the absolute value of those things is superfluous, so we can just take them out of the absolute value, because the absolute value of any positive thing will give you back itself. So that's what that becomes. The absolute value of x over 5 is constant as far as n is concerned, so we can take out the absolute value of x over 5. And then the absolute value of 5, of course, simplifies to be 5. Then the powers in this fraction of n to the 5th over n plus 1 to the 5th. Well, actually, let me rewrite that now so that we're actually making a change there. So I pulled the absolute value of x over 5 out, but what's left is the n to the 5th over n plus 1 to the 5th. And one thing you might remember is that if the powers are the same, we can rewrite that as the quotient n over n plus 1 all raised to the 5th. And we could go inside of that composition and evaluate the limit as n approaches infinity of n over n plus 1, which is 1, and 1 to the 5th is 1. And so we're left with the absolute value of x over 5. Now, for the series to converge, that limit answer, once we have that completely simplified as much as it can be simplified, it will converge when that limit answer is less than 1. Now, that does not yet look like that expression, absolute value of x minus c is less than r. So to make it go there, I'm going to multiply both sides of this inequality by positive 5. And it's now in that form, which means that the radius of convergence for this one is 5. Okay. Now, the third one. So we've got sigma n equals 0 to infinity, negative 1 to the nth times x to the 2n plus 1 divided by 2n plus 1 factorial. Okay, so using the root test, the limit. This is a ratio test. Sorry, I just misspoke. The ratio test, so we'll take the limit as n approaches infinity of the absolute value of that expression after sigma with n plus 1 substituted in for every n make sure you're very careful in doing that substitution. That's what it should look like. And in here, take out the n and put n plus 1 in its place. Should look like that. Okay. Then that's going to be divided by the regular expression with just n in its normal place. Like that. Now, looks like my absolute value needs to be made a little bit bigger. All right, so normally when I'm doing this, after you've gotten some experience, you'll do the same thing. The absolute value of a power of -1 is +1, and so that part I'm just going to strip away and say that the absolute value of those individual items become +1. Now the powers of x are not necessarily going to be positive things, and so we have to leave those inside the absolute value. So I'm going to go ahead and just write this as x to the, let's see, 2n plus 2 plus 1 is 2n plus 3. Just doing that distribution and collecting like terms. And the thing inside of the parentheses that we're going to do the factorial of is also going to simplify to be 2n plus 3. And I also, at the same time that I've stripped away those -1s and kind of simplified the n plus 1 expression, I'm also going to do that division of fractions by multiplying by reciprocal of the denominator fraction. So I kind of do several things at once here. And you're going to want to not skip too many steps, but I think what I've done here, taking away the powers of -1 and doing multiplication by the reciprocal, is something that you would understand pretty easily. So I think we'll be okay. Now, to do the powers of x that are divided, we're going to subtract the exponents to do that division. And x to the 2n plus 3 divided by x to the 2n plus 1 will be x to the 2n plus 3 minus 2n plus 1. So the 2n's go away, and 3 minus 1 is 2. Now, I'll go over to the side here for a second. Remember, when you have factorials like this in a fraction, the idea is you want to take the larger of the two and start expanding it. So 2n plus 3 is larger than 2n plus 1. So that'll be 2n plus 3 multiplied by the next lower number, which would be 2n plus 2, which would be multiplied by the next lower number, which would be 2n plus 1. I'm going to stop there and write factorial to indicate the multiplication of all the rest of the numbers. And then those 2n plus 1 factorials cancel. And so that will become, and the absolute value isn't necessary, by the way. That factorial divided by factorial simplifies to be 1 over 2n plus 3 times 2n plus 2. Okay. Now, of course, the absolute value of x squared, we don't really need the absolute value because we're squaring x, and so it'll be non-negative anyway. But that constant thing is multiplied by 1 over a power of n. If we multiply that out, that would be 4n squared. And as n goes to infinity, 1 over power of n is going to go to 0. And 0 times that constant absolute value of x squared will go to 0. Okay, so that limit is 0. And then we say, well, since we're doing the ratio test, we're going to say, well, that limit answer, when is that less than 1? Okay, that's the ratio test going in. And 0, the answer is always less than 1. And so it doesn't matter what x is. It will simplify to be 0. And of course 0 is always less than 1. And so that means that the radius of convergence is infinite. For all x's that would make that true would be any real number x. And so the radius of convergence is infinity. All right. So now that we've done those radii of convergence, we need to find out whether we have, or what our interval of convergence is. We're going to come back to that in just a second because I want to talk about that idea first and then come back and do these examples. So if you go to the next slide, for a power series whose radius of convergence is a finite number r, which was like r equals 5 and r equals 1, going backwards through the two examples, it doesn't say, as I said earlier, well, what if it is equal to r? So the endpoints of the interval of convergence when r is a finite number has to be tested. So you have to test each endpoint separately, whether it converges or diverges at the endpoints. So there'll be 2 more tests that you have to do after that. So going to the next slide, endpoint convergence. As a result, the interval of convergence of a power series can take any of one of those 6 forms. The radius could be 0 because it only converges at its center. The radius could be infinite, which is like the last one we just did, and that means it converges for all real numbers. So I'm going to go ahead in this example, and I'm going to go ahead and write the answer for the interval of convergence, because whenever the radius of convergence is infinite, that means that the interval of convergence, the real numbers that make that happen, are all of them. Okay, so that's our interval of convergence when the radius of convergence is infinite. Then, since the endpoints may or may not be places, x values that make the series converge, we're going to have to test each one, and there's the possibility of, in the first case, it will converge at neither. It'll diverge at the endpoints, so you'll have an open interval, as you see in figure 9.19. It could be that the right-hand point actually converges, but the left endpoint does not. That'd be the second one. It could be that the left endpoint converges, but the right-hand endpoint does not. Or it could be that both endpoints converge. So it's going to be one of these 6 possibilities. And so, let's see. Let me see if that's the right one. The example 4 reminds me of something we may have looked at, so I'm looking to make sure whether that was one of our examples or not. I don't think it was. No, it was not. So that's a new one. I guess we can go ahead and find the interval of convergence for number 4 as a test run. No, we won't. We'll come back and do that one in the next slide, but I do want to go back and do these intervals of convergence for the ones that we've already found the radius of convergence for, so that we know. So we're actually skipping to example 5, where it says find the intervals of convergence for the 3 power series in example 3. So we've already done number 3. The interval of convergence is negative infinity to infinity. So let's back up one. Let's look at this one. If the absolute value of x is less than 5, then that means that negative 5 is less than x is less than 5 is the inequality we could write for absolute value of x less than 5 without the absolute value. And the endpoints are negative 5 and positive 5, respectively. So I'm looking at that expression of what the series is. So we need to test each of the endpoints. So I'm going to let x equal -5. And I'm going to substitute in for the x in the series formulation. I'm going to substitute in a -5 where that x is. So -5 to the nth over 5 to the nth n to the 5th. Okay? So, because both 5 in the denominator is raised to the nth and -5 is also raised to the nth, those can be combined into a single fraction of something raised to the nth, and that would be -5 over +5 to the nth times 1 over n to the 5th. And of course, that -5 over 5 simplifies. That's -1 to the nth times 1 over n to the 5th. Oops. I wrote 5 too though. Sorry, back up. It's n to the 5th. Okay, so this is an alternating series. With that -1 raised to the nth, we know it's alternating. Since that's an alternating series, we need to identify what a sub n for that would be. It's 1 over n to the 5th. Okay, and test 1 for the alternating series test is, what is the limit as n approaches infinity of a sub n, 1 over n to the 5th? That's actually equal to 0. So that part of the test has been passed. Then we look at a sub n plus 1, which would be 1 over n plus 1 to the 5th. And then we're going to compare that to a sub n, which is 1 over n to the 5th. And since the denominator on the left is bigger than the denominator on the right for all n, the fraction on the left is smaller than, technically, or equal to, the one on the right, and so we pass both tests, and so it does converge when x is -5. Now we need to do a test for when x is +5. Okay, so the series when x is +5 will be 5 to the nth over 5 to the nth times n to the 5th, which simplifies to be 1 over n to the 5th, which is a p-series. Yes, you really need to know all of your tests for convergence and divergence of series, because this is where you're going to get to use them all again. So please be aware that you do need to keep those in your head. P is equal to 5, and since P, can't make that look like an E very well. I'll try again. Since P is greater than 1, that means that this series converges. Okay, now because we know that that converges, we can claim, therefore, that we have convergence when x is positive 5. And so, right over here, this is the temporary answer from this inequality right here, with the absolute value in it removed, goes to up here where the star is, and that's our interval of convergence until we find out whether the endpoints give us convergence or not. And once we've determined that, in this particular case, it's convergent at -5, so we include -5 until we get to 5, and we found convergence there as well. So our interval of convergence goes from -5 to +5, including both endpoints. Okay, now let's go back one to this one. Our kind of thought is this absolute value of x less than 1 becomes this inequality when you take the absolute value away, and that means we need to test the endpoints. So if I let x equal -1, the series will become square root of n times -1 to the nth. And that is an alternating series. And our a sub n would be the square root of n. And first test, we take the limit as n approaches infinity of square root of n. That's infinite. And that means that the alternating series test itself isn't working, except for it did give us some good information. That is not 0. And so we can say that this series diverges by the nth term test. Nth term test for divergence, which we'll just write for short as nth term test. So we do not have convergence when x is -1. Guess I should write that down. So it diverges when x is -1. Okay, now test the other endpoint when x is +1. The series will become the square root of n times 1 to the nth, which is going to be the series of square root of n. And if we try to take the limit of our a sub n, it again is not 0, which also implies that our series diverges by the nth term test. So therefore it diverges when x is +1. So this time it didn't converge at either endpoint, and our interval of convergence is basically -1 to 1, and we've proven that at the endpoints it does not converge, so it will be strictly the numbers between -1 and 1, inclusive of neither endpoint. That's our interval of convergence for that one. Okay, so that's the 3, so that's example 5, basically. We'll come back and do 4 in the next session. So I'm going to end this for now and go on to the next one.